We're going to go and look at another option for integrating. So normally I would start out with seeing if normal integration would work, if U substitution would work. If those didn't work, I'd try maybe longhand division or expanding it if there was parentheses. If that doesn't work, then I might try integration by parts. And if integration by parts doesn't work, then I might go ahead and try that table. So integration by parts is if you have the integral of two things multiplied together, then integral of u dv ends up being u times v minus the integral of v du. So when you're dealing with integration by parts, I'd make sure I have this formula written down at the top of your page. For the most part, you want the antiderivative of v, which is dv, to be something that's relatively easy to find. Sometimes you come across something you can't integrate, so obviously you don't want that to be your dv. You want this integral, once you plug stuff in, to be easier to deal with than your original problem. For the most part, an easy thing to do is to choose u, this part right here, whoops, the u to be the first that shows up in this test or list right here called limit, which is logs. So if you have logs that show up and any of this other stuff, you let logs be your u. If you have um, a polynomial like an x squared and you have a trig function showing up, you often let u be polynomials because that shows up first. So whatever shows up in the first of this list, you let u be that. So suppose we want to go ahead and try to integrate the natural log. And up to this point, we've never been able to take the integral of the natural log. We've been doing the derivative of natural log for quite a while now. So we have our integration by parts formula right here with colors. We have two things. We could either let dv, we have two options for dv. dv could be either your natural log, and you'd have to integrate that to get v, or you could let dv be your dx. However, to be able to find v, we have to integrate. Well, we don't know the integral of natural log. That's what we're trying to do. So it obviously doesn't work to let your dv be your natural log. So we'll let u be your log, which makes sense in the context of what we had up here for lipids. The first thing that shows up is log, so you let that. Well, the derivative of this is 1 over x dx. That means the other part over here, your dx, would have to correspond to your dv, because you have a u and a dv in your problem. Well, then we got to get v to show up. Well, to go from your derivative to v, you have to integrate. Well, when you integrate that, you just get x. So we have to replace u with what we have here of natural log. We have to replace v with what we have of x. And then v goes after your integral sign. And then du, which is 1 over x dx, goes here. So in other words, we get x natural log of x. In this case, what we have after our integral sign simplifies. Your x times your 1 over x is just 1. Now, for the most part, when you're looking at this, you want your integral, after you use integration by parts, to be something that's easier than what you started out with. Well, integrating 1 is a lot easier than what we started out with, so that means we're on the right path. If this ended up being more difficult, like a natural log of x times an x squared, well, that would be even more challenging than what we started out with, so that meant you went down the wrong path. So we integrate 1, which we know is x, still have our plus c. So where does integration by parts come from? Yes, it's a formula that works, but why does it work? Well, you guys are familiar with the product rule. If you're doing the derivative of two things multiplied together, you know it's the first times the derivative of the second, or plus the first times the derivative of this. Oh, I hate it when I get tongue-tied. Well, there's the product rule. You know it, even though I can't say it right now. Well, if you just integrate both sides, so here we'd be integrating our derivative. And then if we integrate this whole side, we could just integrate each piece because it's added. Well, you know the derivative and your integral here on the left undo each other, so we just get u times v. The right side doesn't change. Well, all we'd have to do is a little bit of subtraction, and we could get u dv, that integral by itself, by subtracting this from both sides. And this is your integration by parts formula. So it really comes from your product rule. So looking here, we want to integrate arc sine. Well, here's your integration by parts formula. We have arc sine, and we have dx again. So we're trying to integrate this. Obviously, we don't want arc sine to be our dv because that means we'd have to integrate it, and that's what we're trying to do. You can also think back to your Lipit inverse trig functions shows up. So that's what you want u to be. So your dv would have to be your dx, so you get your integral of that for v to be that. So now you have to do the derivative of the ugly diarrhea color stuff. Well, you should remember that to do something like that, you just want to go ahead and write it like a normal trig function. You know the derivative of sine is cosine. Ah, well, then you'd have to get du by itself. So you'd take your cosine to the other side. Then all you'd have to do is go from here, draw yourself a triangle, knowing that this is angle u, this is opposite of x over your hypotenuse. Then you get your adjacent side using your Pythagorean theorem. And then you're asked to do 1 over the cosine. And so when you do 1 over cosine, looking at your angle here, that's where we end up getting this from. Because remember, cosine would be adjacent over hypotenuse, or just this root, because putting it over 1 doesn't change it. So it'd be 1 over that root, and that's what we have up here. So that's, remember, how to do the derivative of an inverse trig function. So we plug in what our u is, which is your inverse trig, times your v, which is x, according to what we have written down, minus v, which is x. Then we plug in our du, because that's what we have right up here afterwards, du. So we have this in front. Then we have x over this, with a, or you could put the dx afterwards. Now, if it's x over this, that's similar to what we've done before. You should remember that from chapter 4, that we often then did u substitution. So with that, you let u be what's in your root. You'd solve it for your du, you get this. You notice that you only have an x showing up, so you'd want to go ahead and multiply both sides by -1/2. So we'd still have this in front. Do the u substitution here. Replace your red with this, because it would be 1 over the square root of u, which is u to the -1/2. And then instead of writing the blue, which is x dx, you write -1/2 du. So you have multiplying by a number after your integral, you could pull that in front. So we get +1/2, just the integral of u to the -1/2, which you know is pretty easy to integrate. Increase your exponent by 1. Then you have to undo your exponent by putting a 2 in front. Well, your 2 times 1/2, that cancels. And since we started out with x's, you want to leave your answer with x's. So you'd want to substitute in what u is, which is 1 minus x squared, and you would get this. So, looking at this, suppose you didn't pay attention to the limit and you just tried u being e to the power of negative x. So then you do your derivative to get du, then you get this, so that means dv would be x dx, so you get your integral of each one of those, you get 1/2 x squared. Going ahead, plugging in your u, plugging in your v, plugging in your v, and plugging in your du. Well, we can simplify this a little bit. We have a negative and a 1/2 we could pull out. Now, what we have here is an x squared times an e to a power. We started out with x to the first times e to a power. So what we have here is even more difficult than what we started out with. So if you ever get to a situation like that, for the most part, that means you chose the wrong thing to be u and dv. Now, if you looked at Lipit for this particular problem, which is here again, logs, well, we don't have logs. Inverse trig, we don't have that. Polynomial, yes, we have a polynomial. That's our x. So you let u be x, so your dv would be e to that power, that exponential. So you do your derivative of both sides of the purple, we get this. You do the integral of both sides of the orange, we get this. Then you go ahead, plug in your u, plug in your v. After your integral, you plug in your v, and you plug in your du. You can pull that negative out, negative x in front basically there. Pull that negative out after the integral. It's just integrating your e to a power. Notice how now we're just dealing with integrating e to a power versus a variable times e to that power. So this derivative is a lot easier to do. So we can just do our nice normal integration, and we get this. Remember, e to a power is e to that power, and then you got to undo the derivative of the exponent. So instead of adding a negative, we could just write it as subtraction. You could either leave it like that, or if you wanted, you could pull a negative e to the negative x out of here. Either one of these last two lines would be acceptable. So would not make a difference either way. So here is some kind of a cheat sheet for what you let u be and dv in different situations. So here, x to a power times an e, or x to a power times trig, or x to a power times cosine, you let u be that x to the power. Similarly down here, x to a power times natural log, x to a power times your trig, or x to a power times your inverse trig, you let u be this. Or here we go down here, e to a power times your trig, e to a power times your trig. So this last one right here actually goes against the Lipit rule. Now, for the most part, when you're dealing with problems like this, you could let u be either one and it will work. It doesn't really make a difference. So for the sake of this last problem, it matches with what we were doing right here in the bottom, e to a power times your trig. Come on, computer. There we go. So we're going to follow what that cheat sheet says. We're going to let u be your trig, your dv be your e to the power. Now, if you did decide to follow the Lipit rule here, it would work. It would give you the same answer, but your process would be slightly different. So we're going to go ahead and do the derivative of both sides of the orange. So we get 3 cosine 3x. Integrate this, we get a 1/2 e to that power. So looking at your integration by parts, we go u, which is sine. Oh, I guess I switched the order, sorry. Sine 3x times your v minus your u. I switched the order again. Sorry about that. Didn't realize that. There's your du. No, I guess I didn't. And your dv. I'm having a hard time here. Sorry about that. You guys never struggle. Okay, so, well, can't really do a whole lot of simplifying here in the beginning. But you notice you're timesing by 3, timesing by a half. You could pull that 3 halves out. And well, as we look here, we have e to the power times a trig function. It's not really easier than what we started out with, but definitely not harder than what we started out with. So you're probably still doing okay. However, when you look at this, the integral here was very similar to what we started out with. Basically, you have to do integration by parts a second time. So in other words, you'd want to go ahead and do integration by parts in this, figuring out your u, which we started out with u being up here, our trig function, so we want u to be our trig function down here to follow the same pattern. dv would have to be your e to the power. Do the derivative of both sides of your u. Do the integral of both sides of your dv. So we're going to bring this down, we're going to bring this down. Then we're going to go ahead and instead of writing this right here in blue, we're going to use our integration by parts with our blue, our u times our v minus the integral of your v times your du, all coming from right here. So we're still going to just bring this down here in black. So now we have lots of stuff going on here. So you want to take it step by step. We could distribute through your 3 halves onto this. That's where the 3/4 comes from. 3 halves onto this. And you might be wondering, well, why is that a plus? Well, because it's a negative 3 halves that we're distributing through. And then when you look here, notice you have a negative 3 times a 1/2. You could pull that towards the front. So now we're timesing by this negative 3 halves. I'm going to pull that all the way in front of my integral sign, trying to do it step by step to make it a little bit easier. Because I've seen way too many people get this number here wrong because they try to do all pulling this stuff out after the integral sign and distributing all at once and they mess it up. Now, you might be thinking that still doesn't really look any better. Yes, I agree. However, notice with what we started out with here, that's what's showing up after your integral sign. So, side note here, you guys should remember if I said x is equal to 12 minus 9 over 4x, to solve it for x, wouldn't you add that 9 over 4x to both sides? To try to go ahead and solve it, to get all the x's on the same side, and 13 over 4x. And then you go ahead and try to get rid of that timesing by 13 over 4 by doing some division. We're going to do the same thing here. We have what we're looking for, which is highlighted in red, on both sides. So we're going to just go ahead and take this whole thing here to the other side by adding it to both sides of our equation. So over here on the right-hand side, we're only going to have the black because this red stuff cancels out. On the left-hand side, we have one of these integrals plus 9/4 of these integrals. Well, 1 plus 9/4 is 13/4 of these integrals, still equaling what we had over here. Well, now we got to just get our integral by itself, so we'd have to get rid of timesing by 13/4. So we divide by 13/4, or multiply both sides by the reciprocal, which is 4/13. So 4/13 times the whole right-hand side. So we have our indefinite integral by itself now. So we want to make sure we remember r plus c. So here you have a couple options. You could either try to pull stuff out right away, but I think it might be easier if we go ahead and distribute that 13/4 through, 13/4 onto a half, 13/4 onto this. Now I would probably go ahead and pull stuff out. I would probably pull out my e to a power and then pull out my over 13. Over 13, e to a power, and then I'm left with this. So that's what I would get for my final answer.